We previously discussed the local extremum theorem, which says that when local extrema do exist, they can only occur at the critical points and at the endpoints of the domain. So critical points and endpoints or boundary points. But how do we know if local extrema exist at all? So that's the topic of this video. So to begin, let's start with examples where you don't have local extrema. So they're actually easy to construct. It might say, well, how can a function not have a local maximum? Well, suppose that we have a function defined on an open domain from, let's say, 0 to 1. And let's say the function looks like this. Yeah, let me make that a little smoother. Actually, yeah, that's just fine. Okay, so the point x is equal to 0 is not actually on the domain. But as you're approaching 0, it's approaching some output value, let's say 2. And then this is maybe 0.5, something like that. So as x approaches 0, the y value is approaching 2, but it never really gets there. So technically there is no local maximum, because in order for there to be a local maximum, there has to be an actual point at which the function has a greater output at that single point than any point nearby. And this isn't true. You could say, well, what about x is equal to 0? Well, x equals 0 is not a point on the function's domain, so by definition, that cannot be a local maximum. Well, maybe it's a point very close to 0, like 0.1, something like that. Well, if I move a little bit to the left, I get a greater point, so that can't be the local maximum. This point can't be the local maximum. And the same is true of any point on the function's domain. None of the points are at a local maximum. And the same logic applies down here. There is no local minimum either. Another way in which a function can fail to have a local minimum or a local maximum, so I'll just use the same axis. Let's say we have a domain that goes from here to there, is have a vertical asymptote. And so you might say, well, maybe we're failing to have a local maximum and a local minimum because we have, well, first of all, we have no critical points on the interior, and then also we have this open interval. So maybe having a closed interval might help. What if a function is defined on a closed interval? Okay, well, it's the same problem because I can make the function discontinuous. So I can always add a point down here, so I guess that would be a local minimum. Let's stick with the asymptote. So I might have, for example, a vertical asymptote like this. Okay, so this by itself, if I exclude the boundary points, will not have a local min or a local max. But since the boundary points are included in the domain, I'm forced to assign them some value, like this or that. Now this one is a local minimum because if you look at the x values close by, it's this one compared to all these points up there. And this one is indeed a local maximum. So if you compare that one with the x values nearby, these are a lot smaller than this output right there. But if we remove the boundary points, so if we just say that this is defined on an open interval, and we have a vertical asymptote like this, again, we don't have a local minimum or a local maximum, right? Because there's no single point that's the greatest. If I move a little bit to the left, well, without reaching the actual this point right here, which is not a boundary point because that point's not on the domain, but this kind of edge point, I just keep getting larger and larger values of the function. And here I get smaller and smaller values. So these are two examples where we don't have any local extrema. And for a closed interval, well, I can go back to the first one and make this a closed interval. No, because even if I define arbitrarily define this, it's still going to be a local minimum here and a local maximum there. Or if I put a point here and here. I'll just keep that as is. So without getting into too many details of all these different situations, there's a theorem that under certain circumstances will always guarantee that you have a global minimum and maximum. Okay, that's what I wanted to say earlier. If we extend this like that, and even this one, if I put a point here and here, this is going to be a local minimum, right? Because this point is smaller than any of the neighboring points, and this one is a local maximum because that point's greater than any of the neighboring points. Same thing is true over here. If I define the y value at this boundary point to be this y value, and at this boundary point if I define a y value to be that, then this is a local min because the output here is less than any of the outputs up here. And then this one is a local max because this one has a greater value than any of the values down here. So both of these examples, so first of all, we did two examples where we had an open interval and there weren't any local extrema whatsoever. Now I've kind of modified these examples so that it includes the endpoint, and this endpoint and this boundary point we have a local minimum, and at this boundary point we have a local maximum, and the same thing goes here and here. Okay, so you might be tempted. We have one local min and one local max. Well, it must be that the local max is the global maximum, right? Because there's only one maximum, so that must be the global. Wrong, right? Because if this cannot be the global maximum, because here's a point on the domain that's larger than this point. So remember, local just means that if I look in a sliver of the domain, so very close to that point, this is the greatest output value over any of those. Global means consider all of the points on the domain, including the points up here. Well, this point on the domain has a higher output value than this point, so this point cannot be the global maximum. And similarly, this is a local max, but it cannot be the global maximum because this local maximum has a smaller output value than this x value right here, which gives you a larger output value. So both of these, even on the closed domain, there are no global. So now we have a case where we have local extrema, but no global extrema. And basically where this breaks down in both cases is that the function's not continuous. So that's essentially what we get with the extreme value theorem. So the extreme value theorem tells us the following. So if a continuous function is defined on a closed interval, then it must actually achieve its global minimum and maximum at some point on the domain. So in other words, as long as your function is continuous and it's defined on a closed interval, then it will always possess a global maximum and a global minimum. If it's an open interval, well, we saw what happens with an open interval. We can have a function that doesn't have any extrema at all, local or global. And if we define it on a closed interval, we can, so there's the closed interval that we define it on. We can still do the same sort of thing where we just make the function discontinuous at the endpoints, so it's not continuous. Or maybe we can do something that's discontinuous somewhere in between. So suppose we have a function defined on a closed interval, and we have boundary points, and maybe it's discontinuous somewhere in between. So again, there's no maximum point because we're creeping up to this y value without ever attaining it. And there's no minimum point because we're approaching this y value without ever attaining it. So here, we don't have any global minimum or maximum. But the function fails to be continuous. So the requirements to be guaranteed a global minimum and a global maximum are: 1, the function has to be continuous; 2, the function has to be defined on a closed interval. Now that's not saying that you're not going to find functions defined on open intervals or discontinuous functions that have global minima or maxima. This is just in this particular case. If you have a continuous function and it's defined on a closed interval, then you must have actual global maximum and a global minimum. So it's basic, and that's nice because a lot of functions that we'll look at are defined just for some finite domain, and they're continuous. So we have a continuous function defined on a closed interval. It has to have a global maximum, which is right there, and a global minimum, which I'm not sure if it's there or there. It looks like a little bit of a tie. But it has to have some global maximum and some global minimum. So these sorts of functions are actually pretty common in application. For example, maybe this is profit as a function of the price of a theater ticket. So you have a stage show going on, and you have some sort of model that says if your price is between here and here, this model tells you what the profit's going to be. And of course, there might be natural limits on the price, 0 and some upper limit for some reason. Or maybe the seat, how many seats are sold, what the ticket price should be as a function of how many seats are sold. So 0 to maybe there's only 200 seats in the auditorium, so 0 to 200. So there's lots of reasons why you might just get a closed interval for a domain, and we'll study those in detail in the rest of the chapter. So the extreme value theorem is actually a pretty powerful result. That's how we know that when we have a continuous function defined on a closed interval, that it always has to achieve its global maximum and its global minimum. So that's basically the statement of the theorem. So in our next lecture, we'll go back to the local extremum theorem and explicitly enumerate steps for finding the extrema and locating the global extremum of a function, or the global extrema of a function.